Everyone, I'm Grant. I'm going to be presenting my Marvel Rivals match analysis project. So this is my machine learning project that I've been spending some time on over the summer. I've chosen Marvel Rivals as the subject for this project as I play this game quite often. And I've noticed that, there's a lot of data that is being collected on this. And it's really interesting because a lot of the conversations that are happening around performance, what drives wins is not data driven. It's anecdotal. And that's not inherently wrong, but it's interesting that since there's so much data available in the game, not always shared, but still available, that they're not still not using that. So I wanted to take a crack at using Marvel Rivals tracker.gg API to scrape data and apply some machine learning techniques to better my own performance and understand what really drives wins in this video game. So the first part of this is the data pipeline. Like I said earlier, tracker.gg was the driving force behind this data collection. It's a service that provides match statistics for a lot of different games, including Marvel Rivals. We're able to get statistics like win rates and match stats. More specifically, we can get in-depth metrics, including healing, team damage, kill death ratio, and others. These were able to be split out by individual heroes that were played within one match or multiple and then do that for every match. Um, for this project, we had about 125 matches were scraped for 35 users, and 3 additional users had their entire match history pulled. So we were able to get a good amount of data from the API service. However, we did need to take a little bit of pre-processing on that. Although it came over pretty clean, we needed to do some transformations in order for it to work on the machine learning algorithms. So deep duplication, making sure that things were um, match level versus hero level, and creating some feature engineering to capture some of the most important metrics that might not be explicitly found through by just giving it to the model itself. A big thing that we needed to work here was the Cloudflare had bot protections on this API, so we needed to be really slow. Ideally, we would scrape a lot more users than this, but we needed to do like 1 match per second, and there were thousands of matches that we needed to scrape. So it was pretty slow. So that's kind of what limited us in the data, but it did not have the impact that I thought it would because we were able to find some pretty cool stuff. So the big part of this is the EDA, which is driving force behind most data science projects. We found that there was some really interesting splits by hero, user role, or hero role, user, and maps even. That the average healing, the average KDA really differs between these things. So by analyzing this, we were able to assume that there were some interesting split outs the by this. So there was enough variance to be caught from the machine learning models. Um, we were able to understand through this that some machine learning models may need to have users split out from each other. For example, if we wanted to create some personalized recommendations for a particular user, we're going to need to be able to split this out because the data is just too different and by user or even by hero role. So we're going to need to make sure that, when we make specific recommendations, that the data that's feeding that is only specific to that user. So our first method here was an unsupervised learning, and by the title here, it didn't really work the way that we wanted it to work. We initially wanted to see if we could find stratifications in player type, right? If we're able to understand some users are closer to each other than others, to see if there were clusters within the data using hierarchical clustering and k-means. And we found with both methods, just from an unsupervised standpoint, not really effective. With a K of 2, which was our best silhouette score, it only had a score of 0.09, meaning that it was just not it just did not do a very good job at splitting out the data. Hierarchical clustering did not do much better at all. However, when we compared it using an adjusted rand score to the K value, it seemed to be picking up on some of the labels that it was blind to when it was training. Example for a K of 3, it picked up on hero role and user, which there of the training data, there was 3 users and 3 hero roles. So I think it did a really good job at understanding that there were specific split outs by that, and understanding that even when it wasn't directly told that there were split outs. Meaning that, when we're trying to do this analysis, we're going to need to be able to split out by hero role, as there, at the very least, as there are just or at least control for it, because there are just significant stat differences between each of the roles. The next part of this is principal component analysis. It's a dimensionality technique that allows us to summarize a data set using a smaller set of principal components that capture the greater data set's variance. I don't think this was really applicable to our project because of the focus on interpretability of our model. The PCs themselves did a pretty good job at capturing the variance. With PC1, there was about 25% of the variance was explained, 16% with variance 2, and at principal component 13, about 90% of the variance was explained, which is honestly pretty good. And if the target of our project was to just purely predict wins without really doing anything with it, then I think that principal components would be a good idea. However, that's not really the target of our project. It's more to understand why we win, or why there is a high or low probability of doing well. So we just, although it does a good job on the data set, it's just not very applicable to the goal of this project. So our first baseline classifier is the naive classifier, naive Bayes. What it does is it calculates the conditional probability of a win by giving specific categorical hero picks. So, and that might be the specific hero that was picked or their stats related to that. There's a drawback, is that it's naive. It assumes that there's independence, which was certainly not true. However, despite this structural issue, it did a pretty good job at predicting wins, with a score of about accuracy score of the best model being 75%. Multinomial naive Bayes outperformed Gaussian naive Bayes despite the scoping mismatch. Multinomial is more for predicting rates and the number of times that something has occurred, but it still outperformed Gaussian naive Bayes. The predictability of this classifier suggests that there are significant relationships, even with independence assumptions, that we're able to predict the outcome to such a high degree. It speaks volumes about, the relationships that lie within the data. The second classifier that we used was decision trees. The main purpose of this one is to tailor specific models to users. Decision trees give a very interpretable output that can easily be understood by someone who is not a data scientist, as shown on the graph on the right here. It shows, just talking a little bit more about this, the most important value for overall win rates is your KD ratio and KDA ratio. The secondary factors include team level statistics and maybe the amount of damage that you've taken per minute. If you're not being hit and your team is doing well, you're going to win. This might be broad in general, but when you look at specific when you only limit the training data to a specific user, you can get really interesting insights. And that's what we did. And that's what we did in the Grander project. And we were able to find that specific users should be a little bit more aggressive, or maybe they should learn to avoid more damage rather than take more damage. And that leads to more wins, and a higher KDA ratio. For overall accuracy, it outperformed the naive Bayes approach with an F1 score and accuracy of about 80%. So it did a pretty good job despite being a fairly simple model. The SVM approach surprisingly did very well. It basically takes a couple of kernels and quote unquote projects the data point into a higher dimensional space to find nonlinear relationships within the data. We didn't even need to use those kind of relationships. We used a linear kernel, and we tried multiple, and the linear one had the best results. And it got a prediction accuracy of about 87.9% and F1 of 89.1%, meaning that there's really some hard cutoffs within the data set to separate wins versus losses. As shown in the coefficient graph on the right here, KDA, like what we saw before with the decision trees, KDA ratio was very very important. The amount of healing that the enemy team was able to support their own team with was negatively correlated with success. KDA ratio, the number of kills you get, the number of damage, the amount of damage that you do that is greater than the other team's damage, all very important to predicting success. So I didn't really expect much from SVMs, but it did the best at predicting wins, which was of any of the machine learning models that we used. Changing gears a little bit, the deep learning architecture here is we used a multi-layer perceptron with 3 hidden layers and 32 neurons per layer. We used this, the target of this machine learning approach was not necessarily to predict the probability of, or not to predict winning. We were to predict MVP or SVP status. These are classifications given by the video game at the end of the round to say who the most important player was per team. There's always going to be one MVP, the winner, one from the winning team, and one SVP from the losing team. By predicting the probability that any hero is going to get that designation allows us to better understand that particular player's performance in that game. For example, a game that had a high probability of getting MVP, even if they didn't actually get the MVP, means that they did pretty well. And they were probably very close in that assessment. On the flip side, those who have a low probability probably didn't do that well in the game. So it's a great way to have users understand their own statistics beyond just looking at hero win rates. We're actually able to combine a lot of this data into this probability score that predicts MVP versus and SVP status. It did a pretty good job with an ROC score of 88.7%, and our minimized training loss at the 90th epoch was at 0.4. The graph on the right shows the average probability by user. So like we found in the EDA process, the stats differ quite much by role. So it's not good to compare roles to each other, but just multiple users within the same role, as duelists have just an overall higher chance to get SVP or MVP than strategists or vanguards. So from this graph on the right, we can see that user Aridu is better at strategists and have a higher average probability of getting MVP than Black, White, or Yost. And duelists, however, Yost is better than, and Black, White is better than Aridu. For Vanguard, Black, White, and Yost are about the same. Aridu apparently does not play Vanguard, so there is nothing there. So a very interesting way of, it just results in a very interesting way of looking at the data, and when in the hands of a user can be a very cool addition to understanding their own stats without getting, analysis paralysis. It helps naturally use all of those statistics to predict just a single score. So in conclusion, evaluating models across accuracy, precision, recall, F1 scores, there's distinct advantages for different analytical tasks. While naive Bayes was a good baseline, SVM did the best in both F1 score and accuracy. However, decision trees did a really good job with interpretability and offering specific recommendations to users. We also are able to use the probability output of a neural network to augment the user's understanding of their own data by showing them more than just win rates. By combining the hero matches into a probability score, we can understand we can rank, users can rank their own score within themselves, within their the list of all of the games that they have played, to see where did they do the best and where did they not do so great. So very interesting outputs for this project. And I'm excited to work with this data more. Thank you.